let's understand the chi-square test statistic and why is it important to understand that. So we have categorical data, and that's what we have understood. Okay, so we have categorical data. Okay, and that's what we are dealing with. These are not numbers. So here what we do for categorical data, we have count. We count, and there can be multiple categories. For example, if you have a Bernoulli trial, right? Bernoulli trial. So it's binomial. It's binary, success, failure, right? And you remember the generalization of Bernoulli was binomial for n trials. It was binomial distribution, and similarly, the extension of binomial is multinomial distribution, where you have, this is for n trials. So here you have n trials, but here you have only two categories. Here you have k categories, or okay, say k categories. So these are the known distributions. We have studied Bernoulli and binomial in one of the videos. I'll put the link of that in the description if it's not clear. Okay, so in Bernoulli trial we have success failure, like tossing a coin, and if we toss a coin n times, for capturing the number of times or the total number of successes, we have binomial distribution. And similarly, if we have more than one category, then it becomes multinomial, and we have n trials for those n categories. And all this categorical data, because we can have many categories. So for example, if I'm comparing the height of three species of dog, okay, if I'm comparing their weights of 3 species of dog, species 1, species 2, species 3, so there are multiple, these weights will be there. But if I'm comparing some other feature, there is some other feature, and I have the category of that dog, 1, 2, 3, which category this dog belongs to, and I can have only the count, the number of pets people have, okay, what category they have. So if I'm taking that, so I will have only the count of that particular category. So that's where this numerical analysis won't be helpful, or using a t-test or a z-test won't be helpful, and this becomes a categorical data. For example, if you have a male, female, others, gender, we are filling it in a form, right? Then we have to count what is the count of each gender, and depending upon that we make decisions that what is the vacancy, etc., for a job. Okay, so we are modeling this categorical data as a multinomial. So if you know multinomial distribution, so if you check that, the expected value of the ith category is equal to number of, n is the number of trials, right? N is number of trials, n is equal to number of trials. Then the expected value will be n into probability of the ith category. I is the ith category. There can be, I can be 1 to k. Say for example, sigma pi, I, like this is 1 to k. There are k categories. This will, the sum of all the probabilities will be 1. For example, if you have binary and we have heads and tails, and generally if it's a fair coin, then it will be 50-50, half. So the probability sums up to 1. Even if in the multinomial category there can be more than one category, and the sum of all the probabilities should be 1. So your expected value, or for the ith category, or this is also your mean. Okay, this is your mean. Let me write it here. This is the mean, and similarly there will be variance. Okay, variance for the ith category. So this will be expected value of I into 1 minus pi. So this is your npi into 1 minus pi. So this is your multinomial. This is coming from your multinomial distribution. Okay, so we have this. So now again we'll apply central limit theorem for very large n, because this chi-square test is for very large sample size. Okay, we need very large sample size. So we have very large sample size, and now this we have multinomial distribution. So according to central limit theorem, as n increases, this n number of trials increases, this distribution, multinomial distribution, so this will be this is a discrete, right? This is a discrete distribution. So as n increases, we can approximate it as a normal distribution. Okay. So this the observations for each category. So observation for ith category was not theta. So if the observation, whatever is the observation of the count for ith category is equal to OI. Okay, if we are having this, then as n increases, so according to central limit theorem, this multinomial distribution can be approximated as a normal distribution with same mean and variance. So this is your mean, this is your variance. So what will be your, for large n, the count of the ith category can be approximated as a normal distribution. So this is approximation to a normal distribution with mean NPI and variance. This is NPI into 1 minus PI. This is also your expected value of I. Okay, so this is your, this can be approximated as this. Okay, so now we have a normal distribution. We have approximated from a multinomial, we have come to a normal distribution. And as soon as we are normal distribution, we know a lot of things about it. We can do a lot of information. So we have, once we have normal distribution, we can think of z-scores now, what we discussed in z-test video. I'll put the links of those also in the description. So what does the z-score measure? It measures how many standard deviation is a data point away from the mean. Okay, it measures the distance from mean. It measures the distance from mean in standard deviation, in terms of standard deviation. Okay, for a data point. So for example, if I have this, this is your normal distribution and this is your mean, whatever is the mean. And say for example, if I have a data point here, then in terms of standard deviation, how many standard deviations away this data point is. So this, for example, this is your X data point. So how many standard deviations away this data point is, the z-score will give you that information. And then we can have a z-score is a standardized score. Standardized means mean centered and variance scaled. Standardized. This is your, whatever is your expected value, whatever is your observed value minus your expected value by square root of variance of the ith category, right? We divide by the standard deviation. This is square root of variance. So that's what, this is your observed or x bar for sample mean. And here we have counts, right? So this is your observed count for ith category. This is the expected count for the ith category, which I am getting from this multinomial trials. Okay, whatever is the category. And then we have the variance. This is your mean centered and variance scaled. So this is your expected value is your mean, and the square root of variance is your standard deviation. We know this. So we just subtract it from here and we divide it by the standard deviation, and this is standardized now. So this standardized score is called ZI. ZI is equal to observed count of the ith category. We have multinomial data, expected value by square root of variance of the ith category, whatever is the variance. So what are those values? Let's put them and just keep them. OI minus NPI by square root of NPI into 1 minus PI. So this is what we'll get. But there's a catch. So this is your ZI. So we have got a ZI is, so this is standardized means this is your, this will be here N01. Okay, that is mean centered and variance is scaled to 1. So whatever, if I divide by whatever is the variance, finally we'll get the variance as 1. So this is your mu, this is your sigma square. So now we have this ZI. So we came back to ZI. Where are we going with this? So this is your ZI, because your chi-square test, finally the test statistic should be measured in terms of standard normal distribution. So this is your Zi. That's what we did, Zi, standard normal distribution. And the square of those is your test statistic. So we found out that for categorical data, this can be modeled as multinomial, and multinomial as n increases, as n becomes very large and tends to infinity, this multinomial can be approximated as a normal distribution or a Gaussian distribution with the mean and the variance same as whatever we are getting from the multinomial data, okay, from the multinomial distribution. And then we standardize that with the help of the z-score, which measures the distance of a data point from the mean. We standardize it, that is mean centered and variance scale, and after that we have the Zi. But there is one catch for this, is what Pearson did. So there is a lot of mathematical proofs for this chi-square test, that this variance I, okay, instead of using this variance I, what Pearson did, that he provided a proof. I will not provide you that proof, that this can be written as square root of EI. Instead of variance, I can use it as expected value of EI itself. So there is a proof to make, he did to make the math simple. I'll not discuss the proof here, okay. But let's assume that instead of variance, he just put the expected value of E back here to make the math simple. So now my Zi becomes this for multinomial distribution, which is approximated as a standard as a normal distribution, and from there we standardize it, and then this is your standardized standard normal distribution, and this is your basis of your, now we use this as the basis of your chi-square test statistic. So what is your chi-square test statistic? So this is your fancy x square chi-square test statistic. So chi-square statistic is given as I'll use another color. Chi-square, this is calculated, okay. This is a test statistic found by squaring all the Zi's that we have got, and this is equal to sigma Zi square. Zi is this, plug it here, sigma. So for if the number of categories is k, then I is equal to 1 to k, and this is OI, the observed count of ith category, minus EI square, and this EI square root will go off, and this will become EI as it is. So this is your chi-square test statistic. So now we have formulated a categorical data into a chi-square test statistic, and this chi-square test statistic follows a chi-square distribution because of this, and now we can use this test statistic for our chi-square test. I hope this is clear. Okay, so this is your chi-square test statistic also. This is your summation of this, and we found out this Zi, and we plugged in the value here for our categorical data, and we got this formula, and this is the formula that is used. Okay, so now let's, and this is for very large n, the chi-square test statistic, this also for very large n as n increases. So just I'll write a note for very large n, this chi-square statistic, chi-square calc follows chi-square distribution.